Hey guys, this is a pretty meaty problem. So we're given this table here that shows three regions of the Earth, the radius that they go through, and their densities, the inner core, the outer core, and the mantle. And the first part of this problem asks us to use this model to predict the average density of the entire Earth as a whole. Now, the general formula for density is pretty basic, but the way we have to use it in this problem is a little hard. So, the formula for density, in general, is always mass divided by volume. But in the case of this problem, we're finding the average density from three different layers of stuff. So it's not just going to be mass divided by volume, but it's going to be m1 plus mass 2 plus mass 3, all divided by volume 1 plus volume 2 plus volume 3. So we can already see now that the formula is starting to get a little more complicated. And unfortunately for us, it has to get a little bit more complicated than this because we're not given all the information that we need in order to just plug in some numbers. Because we're not given the actual masses of those regions, and we're not given the actual volumes of those regions either. So first off, let's focus on the numerator. So in the numerator, we have m1 plus m2 plus m3. We don't have the masses, but we can figure out the masses by using, ironically, the density equation. Because if density is equal to mass times volume, then algebraically speaking, mass should be equal to density times volume. This is convenient because we can plug this into the top half of the equation for each individual mass. So it's rho 1 v1 plus rho 2 v2 plus rho 3 v3, and then all divided by our same v's. Now that's a little better. Now our formula has some knowns, because we do know the densities of all three regions, but we still don't know the volumes that are at play in this equation. But we can bring another equation in that'll help us. Because another equation that you want to have memorized is if we're assuming that each layer of the Earth has a spherical kind of concentric shape to it, then that means that we have to recall that the volume of a sphere is equal to 4/3 multiplied by pi multiplied by the cube of the radius of that section. So we can account for that in our formula to get rid of the unknown v's. So instead that's rho 1 multiplied by, instead of writing v1, instead we can write rho 1 multiplied by 4/3 pi r1 cubed. And so I'm assuming that the 1 subscript refers to the inner core, which is basically a ball shape. Now let's do the same thing for rho sub 2. And then this is where things might get a little tricky. Be careful here. Because even though we do have an r sub 2, we do have the radius difference for the outer core, we only have the distance. Remember that in this problem, we're looking at multiple layers of the Earth. So if we're looking for just the volume of the outer core, we don't want to just use the sphere formula straight, because that'll give us the volume of the inner core as well, which we don't want. We only want the volume of the next outer layer. Fortunately, though, the formula for just the outer layer is pretty simple too. It's basically just the sphere equation again, except we're subtracting the cubes of the two radii. So instead of just writing 4/3 pi r2 cubed, instead we write in parentheses r2 cubed minus r1 cubed. And that'll work. That is our formula for the volume of the outer core layer. So I'm going to do the same thing for rho 3 times 4/3 pi multiplied by r3 cubed minus r2 cubed. That should be a cube, not a square. Now we divide all of this by v1 plus v2 plus v3. So we basically just rewrite the formulas for volume that we just discussed earlier. So 4/3 pi r1 cubed plus 4/3 pi times r2 cubed minus r1 cubed plus 4/3 pi times r3 cubed minus r1 cubed. So now looking at this, there are a few ways we can simplify this equation, because every single term in both the numerator and the denominator has 4/3 pi. So we can simplify the formula by getting rid of all of these. So now the formula is rho 1 r1 cubed plus rho 2 r2 cubed minus r1 cubed plus rho 3 r3 cubed minus r2 cubed, all divided by r1 cubed plus r2 cubed minus r1 cubed plus r3 cubed minus r1 cubed. And notice that a few of these terms repeat themselves a few times. There's an r1 cubed minus another r1 cubed later on. We have a similar thing going on with... Actually, this one should have been an r2 cubed. We have a similar situation going on with them where they cancel out. So all that's left in the denominator is just the r3 cubed. So now the formula simplifies even further to just rho 1 r1 cubed. Actually, I just decided to write the rest of it out off camera because no one wants to watch that. This is boring. But yeah, this is the formula now. And really, this formula only contains things that we know, because we have the radii from this table here. We know that the top is inner core is 1. I'm using 1 as a subscript for the inner core, 2 for the outer core, and 3 for the mantle. So, and we have the density and radii for all those 3 subscripts. So really, everything in this equation we now know. There are probably a couple other ways you could simplify it, but that's up to you. I think this is honestly pretty good right now. So yeah, so you just plug in the numbers into your calculator, and we find a density of about 5,500 kilograms per cubic meter. And so that is our answer for part A. And you may be a little scared right now, because there is a part B, but don't worry, part B is way simpler than part A, because part B is just asking about the average density of the Earth as a whole. So instead of finding a density where we take all 3 layers into account, we're just treating the whole thing as one layer. We're just worried about the one density, which is just going to be the whole mass of the Earth divided by its entire volume. And that's given to us in the problem. So it's just the mass of the Earth divided by the volume, which in the problem we're actually given the radius of the Earth, 6,380 kilometers. So we're actually going to have to once again pull out the formula for the volume of a sphere, 4/3 pi r cubed. But again, pretty simple formula, all things considered. It's just we're told the mass is 5.98 times 10 to the power of 24 kilograms. And we're dividing it by 4/3 pi times the cube of the radius, which I'm going to write in meters. So that's 6,380 kilometers, or 6,380 times 10 to the power of 3 meters. All of that is cubed. And then we put that into a calculator and find a density of... Your calculator will give you about 5,497.3 kilograms per cubic meter. So that's it. That's the density we find using the one density method, which is really not far off from the density we found using the 3-layer method. Now the final thing the problem asks is for the percent difference. We're looking for now the percent difference between our 2 density measurements. And the problem specifically asks to determine it as a percent difference of our measurement in part A. So that means we're going to take our 1-layer density, subtract it from our 3-layer density, divide all of that by the 3-layer density, and then multiply the whole thing by 100 to convert it into a percentage, since that's how percent errors work. So yeah, so we just put in the numbers we have earlier into a calculator, and then you should get a value of about negative 0.07%. So again, very, very small difference. Both methods work pretty well to give us a fairly reasonable estimate. But yeah, that's it for the problem. I hope this video helped you out. If it did, please subscribe or tell your friends about this channel, because that'll help me out in making more videos just like this one. If you have a request or a question, leave a comment down below, and I will do my best to help you out. And I hope you all have a lovely day. Bye-bye.